The last time we were together, we ended off on stoichiometry, and I did say I'm spending more time on stoichiometry than possibly for many of you is necessary. However, it's a very valuable and very important tool that we need to understand and go through as many examples as possible. Can assure you of one thing: the more examples you do, the quicker you'll be able to go through stoichiometric calculations. And remember, one of the things that we try and do is we're trying to shave off time. So what we're trying to do is we're trying to put like a tabular formation. You'll see that when we do word problems in maths. Tabulating of an answer. It's quicker. It allows us to put it all together in a recipe format and basically construct a matrix and solve what we don't know. That's what we're doing with these. Now, what I said last time is we're going to look at a couple of just some examples of stoichiometric calculations, right? So what you guys should be doing is not only just looking at it, but taking down the notes and then having a look afterwards, putting the notes on it or doing it with me, and just going through the mental process of doing these kind of things. It almost becomes kind of rote actually at the end of the day because we follow the table, right? Let us say they tell us that we've got ammonium nitrate, okay? And this decomposes and it gives us nitrogen, gives us water, and it gives us oxygen, all in gaseous form because the temperature is pretty high when this starts decomposing, okay? So ammonium nitrate, let's just write down the balanced chemical equation for this character. First of all, we've got 2NH4NO3. This decomposes, it's a solid. It decomposes into 2N2 gaseous form plus 4H2O gas plus O2 gas. Okay, and all this happens at a temperature of 300 degrees Celsius. Okay, now what do? We say, well, first of all, what are we given here? And what do we want to find? We are given 50 grams of this substance. And they want to know what volume of gases do we get off this bit of ammonium nitrate. Now, 50 grams, if you go and look at it, it's not very much, okay? Weigh out 50 grams of sugar, flour, butter, whatever you like, anything that you can to look for 50 grams. And you'll get a feeling that it's not a lot of substance. Let's see what happens. So they want us to do that. So what's the first thing we do? The first thing we say is, right, we need to work out the molar mass. I've already done it to save time. It's going to be, I've got 2 times 14 plus 4 hydrogens of 1, okay, plus I've got 3 oxygens, there they are, times 16, and we end up with 80 grams per 1 mole, right? Then we say, right, what's the next step? Is we work out how many moles that is. We say, right, how much have we got? 50 grams gives me how much? Can you see there? It's going to be less. So it's the 50 divided by the 80, right? That's, as I say, that's where most of the mistakes occur in this. So if we just look at it logically and make sure you get that step right, okay? So we get 0.625 moles. Okay, there we go, 0.625 moles, and that then gives us what? There's my little barrier there, my wall. Okay, this gives us, well, what's our recipe? Okay, our recipe that we should have written down in the beginning is 2, 2, 4, 1. Okay, let's go back. So if we've got 0.625, it reacts in the ratio 2:2, which means that represents 2. Therefore, the other side must be 0.625 moles as well of that. And on this side, we've got how much? 1.25 moles. And on this side, we've got 0.3125 moles. How did we get 0.3125? It reacts in the ratio 2:1. So we say 0.625 is a ratio 2:1. So what's the other one? You divide it by half, right? To get 2:1. and that gives us 0.3125. Now, you say, okay, well, that's fine. Now, they've said what? Volume. Okay? They want to know the volume, and they've given us 101,300 Pascal, or 101.3 kPa, and they've told us the temperature was 300 degrees Celsius. What do? Always change that to Kelvin, right? Add in the 273, 573 degrees Kelvin. All right, so what have we got here? We've got the number of moles of gas, and we've got the temperature, and we know that PV equals nRT. Let's do a typical example, right? Okay, P, we say 101,300 is equal to N. Take the 1.25 times R is 8.31 times 573, and we're going to end up with the volume. Just take out the N there. The volume that we're going to get from the 1.25 is going to be 0.058756. 8756, and this is in cubic meters, right? How much of the others do we get? I'll put them in here in blue. So for the 0.625, we get 0.029378. For that one, 0.058756, and this one, 0.01464689. Okay, so in total, if we add all of those three blues together, we get a total volume over here of 0.102 cubic meters, okay, which is a 0.8. Okay, so that's approximately 102 decimeters cubed, which is 102 liters. Okay, so what has happened is this little 50 grams of ammonium nitrate, this little amount has expanded to give us 103 liters. It's 102.8. 103 liters. That's 103 liter bottles that we've got out of that thing. So you can see that a decomposition of a small amount of chemical in a solid form, not only solid form obviously, but just a decomposition of a small amount, right? 50 grams worth can yield an enormous amount of temperature. I mean, what was it? 300 degrees Celsius. That's pretty warm, right? That's the amount of heat that is given off. That we're going to do in the next section. And the volume of gas is 102 liters, right? This is an explosive. That's how it works. What it does is you get that temperature, but you get a rapidly expanding gas. That rapidly expanding gas, it's like the Big Bang. It's how we all started. Well, the universe as we know it anyway. But you get this rapidly expanding hot gas. That occupies the space. Once it can't occupy that space, what happens? The pressure starts building up. When the pressure builds up, things start blowing out. Windows blow out. Ceilings get blown off. Things like that. That's what actually happens in this situation. So, obviously, this is the kind of stuff we need to know in real life situations, because sadly or otherwise, we do have explosives factories. I mean, I suppose we need dynamite for quarrying and stuff, but they're real, they exist, and it's the kind of thing you need to have a good control over. Let us look at another example, shall we? All right, just give me a seckie. Okay. Let's look at a different example. I'm just going to page down a bit here. Okay, I've still got some space. All right. Let us look. They say we mix carbon and we mix sulfur. Okay, and we get carbon disulfide. So let's have a look at the chemical equation. We've got carbon. Oops, sorry, it's still on blue. Let's just change it back so that I can use the other colors for highlighting. Carbon plus sulfur going to CS2. Okay, And we write our recipe is, let's just go and do it in red. 1, 2, 1. Right. Then we put down, right, what are we given? Now they've told us that this is our given table. And obviously, remember, need to find. So our given table here is we've got 48 grams and 384 grams of this. Now remember, they haven't said to us that any of those are in excess. What does the word excess mean? In the key, if they say excess, it means there's more than enough, okay, for the reaction to take place. When they're given 2, okay, usually it's a clue or a hint as to look for a limiting reagent, right? That's the key. So what do? We say, all right, molar mass, right, as usual, is going to be 12 grams per mole, and over here is going to be 32 grams per mole, all right? And we're going to take it from there. Well, let's do the other one is 76 grams per mole anyway. Okay, so what do? We say, all right, 32 grams per mole is our sulfur. Let's now have a look at the number of moles. So, number of moles, we say, right, I've got 4 moles here, right? All right, and over here, I've got 12, right? And at this point, we don't know. Okay? Alrighty ho then. My bad. I put the S2 there. Sorry about that. A 2's over there. So we say, okay, what have we got a situation here? Well, what we've got here is we've got this, haven't we? Right? We've got 4. Now we have to test ourselves and say, is there a limiting reagent here? So into our process, we now want to put into it, okay, a check for limiting reactant or reagent. Okay? How do we do that? Well, let's first of all try and see if we've got, I'm just going to change color here. If we've got 12 of these, how many carbons do we need? Well, they're going to react in the ratio 2:1. So therefore, if that's 2, I'm going to need 6 moles, right? That's the first part. Let's look at the second part. Let's now look at the carbon and say, okay, we start with, we've got 4 moles. If I have 4 moles, how many do I need of the other one? I need 8 moles. So what does it say? It's saying to us that we've got 4 moles of carbon, right? We need 8 moles of sulfur to react with this, okay? We have got 8, we've got more, which means the carbon, that 8 moles, the 4 moles, is all going to be used up together with 8 moles of sulfur, which gives us at the end of the day, okay, this. Okay. We now say, therefore, this is our limiting reactant, so we can continue with 4 goes to 8, right? Or 4 needs the 8, all right? And then this is going to go here, okay, okay. All right, you can see now that the 4 is going to the 8. They're reacting in a ratio of 1:1, right? So what are we going to get out? We're going to get 4:8. This must be in the ratio 1:2 as to 1 on that side. That's our recipe, remember? So therefore, we're going to get 4 moles that side produced, if you like. Okay, and what does that say to us? Therefore, how much mass have we got? Well, 4 moles, 1 mole is equal to 76 grams per mole, and we've got 4 moles. Therefore, 4 times 76 gives us 304 grams of CS2. Okay. Can you see, just by following the table, actually very, very straightforward, right? Let's just do one more quickly of these, shall we? This is also a classic one where they ask the percentage yield of something. Now, what does the concept percentage yield mean? In essence, what are we saying? We're saying if we've got this much of something, right? Never mind what it is, it's something. And we put it into a chemical reaction, into the recipe. So what are we going to do? We're going to react this with something else, okay? This stuff is going to react with other stuff, okay? Now, obviously, we know what's in here, mostly. And if we react it with something, we know we're going to get something out. So, for example, right, we could react a metal with an acid, right? We could react a carbonate with an acid, right? We know we're going to get various gases and various other products given off, right? But if you think about it, let us say that in our product, okay, I'm rather going to draw it as a regular shape as opposed to a lump of product, all right? In our product over here, we've got the chemical, the stuff, all right? But let us say that there is the chemical, okay? That we want to find out how pure this is. What is this piece at the top? Okay. This is our impurities, isn't it? So what do we essentially want to do? We want to extract that out, right? And we want to measure how much of that, how much of the actual chemical there was in the sample. Why do we need to do this? Well, for example, let's think about it. You're a geologist, okay, or you're an explorer with a company, a mining company, and you find copper ores in the soil, right? You want to know how much can you extract out of that? How much is pure copper? How much is just a lump of rock? So you could have very high quality copper, but in a big chunk of rock. So you're only going to get a little bit out of mining tons of rock. So it becomes an economic viability study, essentially, doesn't it? We're looking to see how much is we getting out per ton we're mining. This is, once again, a real life situation. This is what we have to look at. So we need to know, what are we going to get out? Okay, how pure is this? I mean, it would be lovely if you found a whole flippin' vein of just pure gold, and we didn't have to do anything to it to extract it, or platinum, or any one of those metals, wouldn't it? Okay, so let's have a look at this. That's what we're doing, right? So the classic one that they normally ask, the fun one, is the seashells. They've said here, we've got a sample mass of 5 grams. Okay, so conceptually, where are we? And it is wise to do a drawing of this. Conceptually, this here, isn't it? Okay, this is our sample. And they've said the sample mass is equal to 5 grams. So here we go. That's it. That's our sample of 5 grams, right? Well, it's a bit big for that, but let's call it. Okay. This is our sample size. We want to know how much good stuff do we get out. Okay. So we take these seashells and they heat it to 100 degrees Celsius to drive off water and everything else, and it decomposes. So let's look at the chemical reaction for the seashell, shall we? And if any of you want to, you can do that she sells seashells by the seashore thing. CaCO3 is calcium carbonate. CaCO3 going to CO2 gas in this case, plus CaO as a solid, which is the residue left. This is the reaction when we apply the heat to it. And let me put my recipe down, lest we forget. 1, 1, 1. Right? And here is my wall over here. And I'm going to shift up a bit because we're probably going to be moving on to another page. Okay, back to you, like so. Right, CaCO3. What have we got? Now they're given over here is they say this. Given we got 0.66 grams or 0.6 grams of 0.66 grams of CO2. Right? So what are we saying? We're saying that we get 0.66 grams. Now it's important that we understand and we start where we've got the most information. That's what we always do. Most information is there. So let us put down molecular mass of this, and we say, okay, is 44 grams per mole. Okay, 44 grams for 1 mole, right? So therefore, what can we calculate? The next thing we do is we calculate number of moles, right? Same old, wash, rinse, repeat, okay? Number of moles in this case, we say 44 grams is that. We've got 0.66 grams, therefore, how many moles? And the answer comes out that over that. We end up with 0.015 moles of CO2. Okay? So when this decomposed, the reality of it was that we got 0.015 moles of gas given out. Remember, they could have given us the CaO. That's called quicklime, I believe. So what you do is you say, start with the one that you made, because that's what you got, right? That's the actual amount that came out of there. Now we say, okay, using the actual amount, we work backwards, don't we? We say, okay, right, we work backwards, guys. We say to ourselves, right, 0.015 of CO2 should also have given me 0.015 moles of CaCO3. So that's what I actually had, because all I got was 0.66 grams, which is 0.015 moles of CO2 when the reaction was over. So therefore, how much CaCO3 was there to give me that, right? There was 0.015 moles. Then we work out molecular mass of CaCO3, which is going to come to 100 grams for 1 mole. We've got 0.015. That is then going to give us, right, that times the 100 is going to give us 1.5 grams of CaCO3. Can you see that there had to have been 1.5 grams of CaCO3 to have given us the amount of the 0.66 grams of CO2 that we got out? They are linked in the mole ratio. In this case, granted it's 1-to-1, but that is the linkage that we make. So therefore, there was only inside of my sample over here, the chemical, there was only 1.5 grams. And my sample was 5. So the chemical actually was a much smaller bit than I've got there. The chemical was down here. It was only that lump. Okay, let's call it this bit. Okay, the rest of it was impurities as well, wasn't it? So how much is the impurity? Well, what do? We say, all right. Okay, so we say we got 1.5 grams of actual CaCO3 in 5 grams of sample. Therefore, it's 30%. Okay? So, we now know that of this ore body that we're going to mine, of the seashells or whatever, only 30% is CaCO3 in there. Okay? Pure CaCO3. The rest is composed of other materials and things like that. So it's told us that, well, do you know what? If we were mining CaCO3, then we needed it. This is what we would get 30%. And that'll give us, okay, obviously they do lots of tests across the ore body and establish, I guess, pretty much a mean for what it should be. And then they would apply that to the mine and say, right, therefore we're going to be extracting, and then they would design, okay, the extraction techniques. This is the kind of thing we talk about in grade 12. We talk about chemical processes and procedures. How do we set up a plant to actually do this? What should we do? What's the most cost-effective way of doing it? Remember, we've said things before, like you've got to be careful with high pressures, high temperatures, high concentrations and things like that, because you know what? Getting a high pressure is very, very expensive, right? High temperatures, lots of energy associated. So we'll design. That's what the chemical engineers do. They design the processes, the procedures, how and what and where and when, okay? And also the most economic one that we're going to use, right? In the next session, we're going to move on to the bond energies, okay, between the various atoms. And we're going to look at how it actually works. Remember, I've always said that we need this line here, okay? This line, I've always said, is where the magic happens, right? Down there between this side of the reaction and that side of the reaction, right? Because we're going to now look at products, we're going to look at reactants going to products, right? And what happens at this boundary, okay, that we've spoken about repeatedly? The boundary is now the area that we're going to be focusing on. Okay, that's going to be the next session of the work we're going to cover, and I'll see you in that session.